After going through the numerical details in time domain simulations, we can discuss the implementation of nonlinear capacitors. It does not look as straightforward as it is supposed to be, and earlier implementations had led to the charge non-conservation problems. The problem is quite well known today. Reviewing what causes the problem can provide us with insights on the interaction between the models and the circuit simulators. Such knowledge will help us to avoid some obvious mistakes in the future. To begin with, let's look at what is the charge conservation problem. In circuit simulations, charges cannot be generated or destroyed. They can just be moved around as a result of the time evolution of the currents and voltages. That is, the total charge in the circuit has to be constant at all times. This is referred to as the charge conservation requirement. This is implied by the KCL, as the total current entering all nodes have to be zero. There will not be any increment of charge. Let's take a look at what will happen when charge is not conserved. For the simple RC circuit shown here, we apply a continuous pulses to it. If the capacitor is completely charged and discharged, the output high and output low is determined by the input pulses. That is, the output will also be a train of pulses with the same low and high value as shown in the output characteristics here. However, we may observe an increase in the capacitor voltage over time, as indicated by the red line. Such effect is not physical, which is caused by the charge accumulation over time when there is a violation to the charge conservation principle. Let's examine the cause for charge non-conservation. The first possible reason is due to errors in the numerical integration of the branch equations of a capacitor shown here. Let's consider the total charge at time t(i-1), which is given by the sum of the charges stored at all the nodes of the circuit. Assume the charge conserved from time t0 up to this point. Then, Q at t(i-1) will be the same as Q at t0. Now, let's look at what happens at time ti. Its total charge is equal to the total charge at ti-1 plus the time step, which is represented by hi, times the sum of the total currents entering or leaving all the nodes. According to KCL, this sum should be zero. Therefore, Q at ti will also be equal to Q at t0. However, during the iteration process, the simulator may not be able to have the sum of all currents to be exactly zero. The iteration will stop when the sum of currents is only close enough to zero. In the original spikes implementation, it is controlled by the parameter ρ that represents the relative tolerance of the iteration. Sometimes, we may not want ρ to be too small, as it will require a large number of iterations. Unlike currents which is instantaneous, charge will accumulate over time. If the choice of ρ is not small enough, the error will also accumulate over time. A more important cause of charge non-conservation is coming from the implementation of the branch equation of the capacitor itself. If we look at the branch current of a capacitor, it is given by the time derivative of the charge. We can apply chain rule and express the current as the capacitance times the time derivatives of the voltage. In this case, the characteristic of the capacitance as a function of voltage is used to describe the capacitor. For example, if backward Euler is used to obtain the solution of the current at time ti is given by the equation shown here, in terms of the branch voltage. Let's look at what is the problem in such an implementation. Assume a ramp up and ramp down voltage as shown in this figure is applied to the capacitor as an input. Also assume that the time interval is the same and equal to h. We can relabel the time in terms of h as given here. It is also given that the nonlinear relationship between the charge and voltage is shown in the figure below. Let's calculate the current at time t1 using the Backward-Euler equations given here. So, in the ramp-up process, the current at t1 is given by the capacitance at t1, which is indicated by the slope of the graph when the voltage is equal to Vx. So, the expression of current at time t1 is given here. The charge accumulation during ramp-up is then equal to C at Vx times h. To calculate the current at time t2 after ramp down, we use the same Backward-Euler equation. But now, we use the capacitance at time t2, which is the capacitance when the voltage across it is 0. It is given by the slope of the graph at V equal to 0 as indicated here. Therefore, the current in the ramp down process is given by the capacitance at 0 volt divided by h and multiplied by minus Vx. As a result, the charge accumulation during ramp down is given by negative C0 times Vx. As C0 and CVx are different, the charge accumulation during ramp up and ramp down cannot cancel out each other, and the overall charge does not conserve. In this example, the problem is caused by the uncertainty at which voltage we use to calculate the capacitance. You may notice that the problem will go away when the Capacitor rule is used, because it uses the average value of the two capacitances. But such an implementation is not robust enough, as sometimes we need to use different multi-step integration methods to achieve accuracy and stability. We can also look at the problem in another way. For the branch current equation here, if we express the characteristics of the capacitor in terms of its capacitance, the charge at a given time t will be expressed as the capacitance at the given bias voltage times the voltage across it at that particular time. Using the product rule, the equivalent branch current equation is given here. The problem comes from the last term, which can be non-zero as the voltage is implicitly time-dependent. In the case of linear capacitor, it is not a problem because this term goes to 0 with a constant capacitor. So, to avoid the problem of charge non-conservation, one approach is to describe the characteristic of the capacitor in terms of the charge it contains rather than its capacitance. And we change the circuit element to what is shown in the figure here. Then, the current will be directly derived from the time derivative of the charge, and the capacitance becomes its voltage derivative. In such a case, let's study what happens when the previous ramp voltage is applied to the capacitor. By using the stored charge as the state variable, the Backward-Euler equation becomes what is given here. During ramp up, the current is then given by QVx divided by h, and the charge increment is just Q at Vx. After ramp down at time t2, the branch current at time t2 is given here. We can see that the charge increment is just minus QVx. As the charge is directly expressed in terms of voltage, the same increment of charge is guaranteed with the same incremental voltage. So, the implementation guaranteed the conservation of charge. As a result, a capacitor should be thought of a charge storage element instead of a capacitor in circuit sense. Today, almost all capacitors are implemented as a charge storage element with an explicit expression of charge as a function of voltage. And the capacitance is obtained by differentiating the charge with respect to the voltage across it. When compared with time-invariant elements like nonlinear resistors, charge takes the role of current, and capacitance takes the role of conductance, which are the first derivative of the state variable. In order to perform circuit simulation with the nonlinear capacitor, we have to represent the capacitor with matrix entries of the system of circuit equations. So the next task is to convert the knowledge we have to the matrix form. However, the exact matrix entries depends on the integration method. Here, I will use the trapezoidal rule as an example, as it is the most popular implementation. I will leave the other forms for your own exercise. Solving the current as the time derivative of charge numerically using trapezoidal rule, we can obtain the currents at the time Ti given by this equation here. The second term in this equation only depends on the quantity at time Ti minus 1 that have been solved already. So it can be regarded as a constant current. The first term is a function of the iterative value of the voltage at time Ti. So it can be regarded as a nonlinear resistor that we have learned before. We can follow the same approach to linearize the nonlinear resistor using the same equivalent circuit given in earlier presentation. The value of the conductance and the equivalent current source is given by these two equations here. The evaluation of these two equations is a bit tricky, and let's go through it together. First of all, there is a current derivative with respect to the branch voltage. We can perform the differentiations to obtain the following equations. The derivative of charge with respect to the branch voltage is just the capacitance. So, the equivalent conductance can be expressed in terms of the capacitance times 2 over H. For the equivalent current, we first replace the current term with its expressions given by the trapezoidal rule above. Then, replace the current derivative in the same way as in the equivalent conductance. We can then have the following equations. In these equations, the equivalent conductance and current source are expressed in terms of branch voltage. It is sufficient to describe the circuit property, but it cannot be directly placed into the circuit matrix for simulation. To do that, we have to apply KVL to convert the branch voltage into individual node voltages. After doing so, the expressions become the following. Here, V plus denotes the voltage of the positive terminal, and V minus denotes the voltage of the negative terminal. The process is a bit tedious, but it is quite straightforward as long as you follow the given procedures. After this, you can put the entries into the circuit matrix, and it looks like the following. I want to remind you that this matrix is for iteration. So, all the values of Q and C are evaluated with the given node voltages at time Ti after the kth iteration. And the simulator will try to find the next voltage values at time Ti for the k plus 1th iteration. Also, these matrix entries for a nonlinear capacitor are not unique and depends on the integration method. So, you should learn the procedures to obtain the entries instead of remembering the actual entries given here. In many cases, we have multi-terminal devices like transistors. Charge can be stored at each of the terminals, and the charge can be controlled by more than one terminals. Let's use a simple circuit here to illustrate the concept. We can connect three capacitors together as shown in this figure. If we treat the internal structure of the capacitor connection as a black box, then it is a charge storage device with three terminals. And there are three terminal charges associated with it that we call Q1, Q2, and Q3. Each of these charges is a function of three voltages, V1, V2, and V3. At each node, we can measure a capacitance, which is the amount of charge increase when the node voltage changes. For example, at node 1, the observed capacitance is called C11, which is defined as the increment of charge at node 1 as a result of voltage change at the same node. With the example circuit, it can be expressed in terms of C1, C2, and C3 as shown here. We can find the capacitances at node 2 and node 3 in the similar way. In addition, the charge stored at node 1 will also be affected by the change of voltage at node 2 and node 3. So, the partial derivatives of Q1 with respect to node 2 and node 3 are not zero. These derivatives are called the transcapacitance, and there are 6 of them, as given here. If you remember there are transconductances, it should not be surprising to see transcapacitances. For a n-node device, there are n squared that many capacitance terms total. Again, what we care about is how a multi-terminal charge storage device can be entered into the circuit matrix for simulation. Similar to the case of two-terminal nonlinear capacitance, the entries depend on integration method. And we will again use the trapezoidal rule as an example. For charge conservation consideration, the terminal charges should be used as the state variables. When the values as functions of terminal voltages are given, the terminal currents will just be the time derivatives of the terminal charges. We have to pay a bit attention here, as the variable V is now a vector, because the terminal charges are controlled by more than one voltage. Applying trapezoidal rule to the branch equations, we get the following expressions. Again, we can identify the constant current part and the voltage-dependent part after applying the trapezoidal rule. Following the same approach to handle multi-terminal nonlinear circuit elements covered in earlier presentations in the series, the general matrix entries for a n-terminal device is given here. And the current voltage relationship at time ti is given by these equations from the trapezoidal rule. So, substituting the known current expressions to the circuit matrix, it becomes the following. By replacing the charge derivatives with the transcapacitances, the matrix can be simplified to the final form as shown here. After a long process, we finally obtain the matrix entries of a multiple terminal charge storage device. The maths may be very confusing, but the concept is quite straightforward. I hope you did not get lost in the process. This presentation put an end to the transient simulations. I will move on to frequency domain simulation in the next presentations.